We have just been looking at how motions of the wheels will result in motions of the robot coordinate system. And in this case, I'm now using a little index R to indicate that we are talking about the axis of the robot coordinate system. We are now interested in computing how motions in the robot coordinate system translate to motions in the world coordinate system. Particularly, we would like to compute where the robot is in the world in world coordinate systems. In Webots, the world coordinate system is centered around the start line. This is how we have set up the world. I show here the coordinate system of the arena, which has the same orientation, and what you can see is that the Webots world coordinate system has its positive x-axis going along the start line, and the direction that the robot will drive along the line is the y-axis of the world coordinate system. When you look at this more carefully, you will see that the robot is essentially rotated around the z-axis, and both coordinate systems have the same z-axis. They are in alignment. Now, if I turn the robot a little bit to the right, you will see this a little better. Now you see the robot coordinate system and the world coordinate system, and in this case, the robot is rotated by positive 90 degrees along the z-axis. Now, to make this a little easier, let's look at this from above. And in this case, we have the z-axis coming out of the plane, and we can focus on the robot coordinate system and the world coordinate system. And we can see that the angle of these are about 135 degrees in this example here. It is a little easier to look at smaller angles, so we can do better geometry and not get hung up with these larger angles. So in this case, the robot coordinate system is rotated by 45 degrees from the world coordinate system. Now let's recall how a point is represented in a coordinate system. And in this case, this could either be the motion of the robot, so the next point the robot has moved to, or it could be a sensor reading from a distance sensor mounted on the robot. And what you will get are values in the robot coordinate system. So you will get the value of the x contribution in the robot coordinate system and the value of the y contribution in the robot coordinate system. So we introduced earlier this idea of using coefficients to basis vectors, and in this case C1 would be the contribution of along the x-axis, C2 would be the contribution along the y-axis, and C3 would be the contribution along the z-axis, which is 0 here. Now what we're interested in is a representation where we could plug in a point like this that is in the robot coordinate system, and that's why I put a little sub-index R to the left here, and turn it into a point in the world coordinate frame. And here you can already see what this means. The point here has different coordinates in the world coordinate system than it had in the robot coordinate system. And in order to see that, you just have to take a straight line down until you hit the x-axis of the world coordinate system. This is the value we are looking for, and a straight line to the left here until it intersects with the y-axis of the world coordinate system. And that is the value we would be looking for that. Now, how to do this? One basic approach would be to look at the geometry, and you can see that this point here is essentially this line minus that line, and we can compute this line as being the adjacent in a triangle that you can see here, and I drew again over there. And that triangle has an hypotenuse, which is the x contribution in the robot coordinate frame, and has an adjacent which is one component, and that's why I put a little 1 here, in the world coordinate frame. So we're talking about this distance here, which we can compute by looking at this triangle, and we all know that cosine of alpha is the adjacent divided by the hypotenuse, and we can now easily solve for the adjacent and compute this number. Now we can also look at the other triangle, which is above here, and in that case you see it has an angle alpha here, and this hypotenuse now is the y-axis contribution in the robot coordinate frame, and from that we can compute this little distance here, which we need to subtract. So with that, we found quite cumbersomely an expression for this point, which is the contribution on the x-axis in the world coordinate frame, one taking the x-axis in the robot coordinate system, the other one taking the y-axis of the robot coordinate system. So you can do this for all the three entries that you're interested in, that is the x, the y, and the z, and the result will look like this. So now you can see I have to multiply the first component of the point in the robot coordinate system, xr, with cosine of alpha, then I subtract sine alpha times the second component, which is yr, and I don't have a z component, which is why I have a 0 here. You can apply similar reasoning to solve for the y component, which is that row, and you will see very quickly that the z component is 0, 0, and 1, because we are only taking the z component from the robot coordinate frame, which is the same, if there would be any, as the one in the world coordinate system. Now there is a better way to do this, and the fundamental way of doing this. And for that I want you to recall real quick that this kind of rotation matrix actually is a set of basis vectors. And in this case, what we have done is we have expressed the robot coordinate system in the world coordinate system. So this is dependent on the angle alpha. So when you would turn the robot coordinate system back to align with the world coordinate system, alpha would be 0, this entry would be 1, this entry would be 0, this entry would be 0, this entry would be 1, and you would be back to normal. Now as you turn this coordinate system, the projection of the x component of the robot becomes smaller, and you can see how eventually x and y just switch positions when you are at a 90-degree turn. Now with that intuition, there is a simple formula to actually compute this projection, which is known as the dot product. And for that we have to actually recall that these basis vectors are of length 1. That means when you look at the dot product definition, the dot product of two vectors is the cosine of the angle between them times their length. Their length is 1, that means this all goes away, and we are essentially looking at the cosine of the angle between them. In order to build this matrix systematically, what you do is you look at how the x-axis of the robot is projected onto the x-axis of the world, then how it projects on the y-axis of the world, and finally how it projects on the z-axis of the world. For the second column you do the same thing, but this time for y of the robot coordinate frame, and project it to each of the world coordinate axis, and finally you do the same for z. Now let's do this real quick. xr dot product of xr with xw is the cosine of alpha of the angle between them. Let's look at xr, this is here, and xw is here, so we can see there's an angle alpha between them, so the entry is cosine of alpha. Let's look at the next one, which is this one, xr dot product with y in the world coordinate frame. So xr is here again, yw is here. Now what is the angle between them? It is 90 minus alpha, which is the cosine of 90 minus alpha is sine of alpha. Third one, xr dot product with the z-axis. What's the angle between them? The angle between them is always 90 degrees. Cosine of 90 degrees, always 0. Now let's go to the second column, and this time we are taking the y-axis of the robot coordinate system and project it on the x, the y, and the z-axis of the world coordinate system. First one is y of r to x of w, and here the angle is 90 plus alpha. Cosine of 90 plus alpha is minus sine of alpha. Next one, yr onto yw, angle is 90, so we just put the cosine of alpha down. Third one, yr dot product with the z-axis of the world, always 90 degrees, so cosine of 90 degrees, 0. Now we do the same thing, but the other way around, starting with the z-axis times the x-axis, it's always going to be 0. times the y-axis, all is going to be 0. And now the dot product between the two z-axes, the angle between them is 0, and cosine of 0 is 1. So the interesting thing about this is this always works, and you can very quickly derive those kind of rotation matrices by following this textbook approach of projecting individual coordinate axes from one system onto all of the coordinate system of the other. Now the next step is to actually compute how motions in the robot frame would convert to motions in the world frame. And in this case, we plug in the delta x of the motion. There is no delta y, there's no delta z, and work out these equations. And as we do that, we see that the second column is essentially not used because it always multiplies with 0. So we get two very simple equations that we can plug into Python and run directly in Webots to compute the x position of the robot in the world coordinate system. And I've done this here for you to make things a little simpler. And what I'm doing is I take the old x position in the world frame and I add the contribution that comes from the forward motion delta x by multiplying it with cosine of alpha. I do the same for y. This time it's sine of alpha. And then I update alpha by adding the rotation that the wheels induce on the robot to the current orientation of the robot, and then I can start over and compute the next incremental motion. Once you implement the equations, this should look like that. You have the robot going around, and now instead of printing the odometer, you print the actual location. And as you can see, the x-axis here is still 0 because the robot is moving forward and stays put, it doesn't move to the right. The y-axis is moving up to 55 centimeters, and you can actually compare this in the scene tree where you can see the ground truth of where the robot is. And indeed, we have something very, very similar as of what we computed using the odometer. Also, we still have 90 degrees, and here you see the rotation to be 001, so around the z-axis, by 1.5708, which is half pi. Now, as we keep going with this, the robot will make its turn. Now it's at 0 degrees, and you see the first errors are accumulating. And as it comes back to the start line, we would expect to be at around 0, where it has started. And you will see that there's a tiny error which comes from all the accumulated rotation errors. Alright, the robot is arriving. It's getting close to 0. And we see that there's something like 10 centimeters, 11 centimeters overshoot. And this should be 360 degrees, but it's only 305 degrees. But we should be pretty happy with this after a 3 meter overall trajectory.